Welcome back, everybody, to the final installment of the Let's Model Things in Spreadsheets series that I've been giving at our PD sessions. Today, we're going to take a step back from physics examples, and we're going to use biology instead. We're going to first take a look at the idea of carrying capacity, and then we're going to take a look at predator-prey models. But first, to start, carrying capacity. It's usually given by a set of complicated expressions that yield this S-curve, where we begin with something that looks like exponential growth, and then we begin to level off based on available resources. Again, the expressions are more complicated than the typical high school student would actually have experience with, but if we take a step back one more time and use the spreadsheet to help us, we can break down this complicated idea into a simple one where the change in population is equal to the current population times a set of modifiers. Let's take a look at how we can do that now.
Okay, so let's begin with a population of rabbits that would have a growth rate and take a look at its change in population. We will start with 100 rabbits, and we will assign a growth rate of 0.3. The logic behind using a decimal here is that you want to think of small time steps. You don't want a model that waits an entire year to update because a lot of change can happen then. So we want to think of it as how many rabbits are born in 1 month, in 1 week, in 1 day. That way we can capture more of the dynamics. As was already mentioned, we can model the change as just the product between rabbits and growth rate. Apparently, Google Sheets already wants to do that, so I will let it. So we see that the change in population for this particular time step is 30. So now we need to see how many rabbits do we have at the beginning of the next time step. Well, that's just, we started with 100 and we gained 30, so we currently have 130. The reason we like spreadsheets is because we can drag ideas down. So this was just a hard-coded value, it drags down. This was a formula, so it also drags down. And we see in the next time step, we have 39 rabbits gained instead of only 30. Well, let's drag this entire idea down so that we have about 30 time steps. And let's add that in. Time. And drag this down as well. And now we can make a graph. And this is what any population would look like if we were not being realistic and taking into account that there is a carrying capacity. There is a cap to which an environment can support something. So we'll take a look at that now. Let's make a new sheet. In fact, let's just copy over these ideas. What we're going to do, however, is we're going to add in another idea. We'll call this carrying capacity, so we'll call it carry cap. And up here, I'm going to call this whole section modifiers. Again, we want to take our current population and multiply it by all of our modifiers. So we're going to add these two up and then perform the multiplication. So here, we'll once again start with 100 rabbits, and we'll once again have a growth rate of 0.3. Now, how does a carrying capacity work? Well, think of it as a percentage. We want to have our current population divided by our max population. That way we have a percentage of our total. The idea is that when we reach the cap, we can't keep growing. So this is a limiting factor, which means we want to have a negative sign here to say prevent growth. Now we'll take a look at the change in population. Again, it is the product of the current rabbits times all of our modifiers. So we're going to add up all the modifiers and take a look at that. As we can see, we only get 20 this time as opposed to 30 in the previous example. Now, once again, the next time step will be the 100 plus the change in population. And we can once again drag this down and see that the changes are, again, not nearly as severe. We went from 30 to 39. Now we go from 20 to 21.6. So let's drag this down. And once again, add in our time so that we can make a proper graph. And we can clearly see that we have this leveling off. Now, one strange thing is I said that carrying capacity was our current population divided by our cap, but we capped at 300. The reason that we capped at 300 is because we're missing something here. Not only is it a percentage of what our carrying capacity is, but we have to compare it to the growth rate. We're only growing by 0.3. Here, by just looking at this percentage, it's basically assumed we're growing by 1. So if we make this one simple change of multiplying by the growth rate value and dragging that down, now we have what we expected all along, that we would cap out at that 1,000, which is what we typed in earlier. So the idea is that carrying capacity is a percentage of your total population times the rate at which you grow. You get this nice little S curve, and we reach 1,000 without actually passing it. So now let's take a look at what happens when we add in some realistic randomness. This is perfect, but that's not what nature looks like. So let's bring these over and add in a column, and we'll call this random. And just to make sure that everything is clear, extend our modifiers caption here. Keeping everything as consistent as possible, 100 rabbits, a growth rate of 0.3. Our carrying capacity will limit us by being negative. It's a percentage, our current population divided by our maximum population, and compared to our growth rate. Now, random, Google Sheets has a rand function, which generates a random number. So if I copy and paste over and over, I keep getting a random value between 0 and 1. But I want this to be plus or minus. So let me just subtract a random number from a positive random number. Now, if I copy and paste randomly, we can see it cycling through some random positive and negative numbers, which is exactly what we want. So now we can take a look at our change in population, equal sign, rabbits, our current population, times the sum of all of our modifiers. And now we have an enormous growth in this example. So the next step would have 100 plus our 62 equals. All right, so because I entered another equation, the random number updated again. And it's very interesting that it took our population and made it negative now all of a sudden. But remember, that's just our change in population. So it's 100 minus 38 equals 61. So it's not that our population is negative, just our change. And we'll see what happens as we drag this down. And we watch our numbers change every single time I type something in. And when we make a graph, we get something that looks actually quite horrific. The randomness you can't even tell this was supposed to be that S curve or that we're supposed to settle around 1,000. It doesn't look like that at all. It really just looks like our random parameter is too strong. So let's go in here, and instead of it being -1 to +1, let's just divide it by 10. See, make it less strong, and then take a look at what happens. Now we can see that growth ramp up and that we level off somewhere near 1,000. Again, I'll just copy and paste. It'll re-roll the idea, and we can see all of these different random curves that all start by growing upward and then leveling off and dancing around 1,000.
All right, so hopefully after that, we're all thinking to ourselves, this is digestible. This is something that can be done in the classroom. So, of course, it's time to kick it up a notch. This is typically what a college level student would see when asked to study the Lotka-Volterra model of predator-prey interaction. This doesn't even have a solution for what the population of rabbits looks like and the population of foxes. You have to use it from this base form, and there's no functional equivalent. So we're not going to let that stop us. We're going to continue to use the idea of the spreadsheet, just doing little jumps and changing the population and adding that to the original from the previous step. So how do we go about doing that? We'll just continue the trend of copy and pasting over. To add in a new fox population to counteract the rabbits, we'll copy and paste the ideas of growth rate, carrying capacity, and randomness. The only modification we'll really need to make is that foxes go up based on the rabbit population, and rabbits go down based on the fox population. And that's what makes it predator-prey. One gains while the other loses. So let's return to the spreadsheets and see how easily we can model this.
So now let's add those foxes in. So we'll make a new sheet. We'll go back here, and we'll grab everything, just like we previously did, paste it in. Now, what we need to do is make sections for rabbits and sections for foxes. So I'm going to add a column to the left, and we'll call this foxes. I'm going to add another column to the left and call this predation, because we're going to lose population due to predation. But I also need to make this entire section for foxes. And now we're going to have, again, a change in rabbits and a change in foxes. So we have this idea for rabbits, rabbits, and rabbits, and then again we have foxes, foxes, and foxes. This is actually really difficult to keep track of, so let's make this a little bit easier. So population, change in population. We will merge this. And we will color code it. So let's take all of our rabbit ideas and color them blue. Let's take all of our fox ideas and color them red. Now it's far easier to follow what's going on. We have blue rabbits and we have red foxes. So let's, once again, start with 100. Our growth rate will be 0.3. Our carrying capacity will be negative to limit our growth. It is a percentage of our current rabbits divided by our maximum population times our growth rate. Random, and let's make sure we do that random divided by 10 trick to keep everything small. So rand minus rand divided by 10. And how many rabbits are eaten per fox? Well, let's just make up a number. Again, we're thinking really small numbers. So just for the sake of the example, let's pick 0, 0, 1. And again, it's based off of which population? The fox population. So I'd have to multiply it by foxes. And let's say that we only start with 20. So we start with 100 rabbits, we start with 20 foxes, and this is what modifies the rabbits. Again, predation for rabbits is negative. We are losing rabbits, but we are gaining foxes. Now, the growth rate of foxes, naturally, without rabbits, foxes would actually decay. So just to keep our numbers similar, let's pick just the opposite. Rabbits grow by 0.3 and foxes die by 0.3. Let's pick the exact same carrying capacity, keep as much the same as possible. So equal sign negative percentage of our current foxes divided by our cap foxes times the growth rate. That came out positive because I have a negative sign here. So let's make sure, just by checking the spreadsheet, that carrying capacity is negative. These are things to point out to our students. Again, let's add our random minus random divided by 10. And predation will have the same idea of predation, but with a positive sign. We're going to gain 0.001 times our rabbit population. So now, equal sign rabbits times the sum of all of our rabbit modifiers. And change in foxes is current foxes times the sum of all of our fox modifiers. And we see that we actually are losing foxes in the beginning and gaining rabbits. Interesting. So equal sign 100 plus the change equals sign 20 plus the change. Now let's grab everything else, drag it down, and now we can drag everything down for 30 time steps again. Let's give ourselves some actual time steps, and then we can take a look at a graph. All right. Maybe not what we were expecting. We have the increase and a decrease, and it looks like it's coming up again. We have a decrease and then an increase, and it looks like it's coming down again. It looks like something interesting might be happening, but we didn't let the populations grow for long enough. Let's take a look at just randomizing some of these values as I copy and paste. All right, so we can clearly see an increase and a decrease and then a turnaround. Let's take the population a little farther. Let's drag it down to here. And make a new graph with double the amount of time. Now we can clearly see this idea of an oscillating population where we have growth and decay of both foxes and rabbits. So neither one explodes, neither one even reaches the carrying capacity, but the two populations tend to dance with each other, increasing and decreasing with a little bit of a lag. When the rabbits begin to grow, shortly after the foxes do begin to grow as well. And when the rabbits begin to decline, because there are too many foxes, we have the foxes begin to decline as an answer, as a response.
So let's recap. We've taken a look at carrying capacity, and we've looked at predator-prey models. Now, at the high school level, we absolutely do see carrying capacity, but you don't really see predator-prey. And it's because you can't break it down any simpler than this. However, by using a spreadsheet, we were able to take both concepts and turn them into something very simple and very similar. The change in population is equal to the current population times your modifiers. They can be growth modifiers, they can be decay modifiers, and that's what creates that fluctuation in the populations. Now, if you would like to see more examples in biology, chemistry, or physics, you know what to do. Like and subscribe, and I'll see you next time.